Okay, we'll get back to section 4.3. And so far we've just looked at the first derivative test. And now another thing that we're going to have to know in this section is called the concavity test. Okay, and so I'll talk about that in just a moment here. Let me start off with a definition, which says that if a graph of a function f lies above all of its tangent lines on an interval I, then it is concave up. CU means concave up on that part of the graph. Okay, if the graph of a if the graph of a function lies below all of its tangent lines, then we say it is concave down on that part of the graph. Okay, so CU is concave up, CD is concave down. That's what the book will be using also. So here's an example. State the open intervals on which the function is concave up or concave down. Well, let's see here. So if we state where it's concave up. Now I'm looking for places on the graph where I would be drawing tangent lines, and all the tangent lines have to be below the curve. If I'm between 2 and 4, and I draw a tangent line anywhere that I draw a tangent line is going to be below the curve. Okay? And so that would indicate that I'm going to be concave up on that part of the graph. Now, where else would I be drawing tangent lines below the curve? If I'm between 6 and 8, and I draw a tangent line anywhere, it's going to be below the curve. And so that would be the other interval where we would be concave up. Now, where we concave down? Well, concave down means that you'd be drawing tangent lines above the curve. So if we're between 0 and 2 and we draw a tangent line, anywhere that we would draw a tangent line, it would be above the curve. Okay, also if we're on the interval 4 to 6 and we draw a tangent line, it's going to be above the curve. If we're on the interval 8 to 10, which is right here, we draw a tangent line, it's going to be above the curve. And then if we're on the interval 10 to infinity and we draw a tangent line, it's going to be above the curve. Okay, now with this graph, at this spot here, I intended that for that to be a sharp turn, and so there's going to be a vertical tangent. Okay, so I wouldn't want to just say concave down on 8 to infinity. You know, I'd want to split it at 10 so that it's written as two different intervals there. Here's the concavity test. Let f double prime exist for all x on an interval I. Okay, item 1, if f double prime of x is greater than 0 for all x on that interval, f would be concave up on that interval. Item 2, if f double prime of x is less than 0 for all x in the interval, f would be concave down on that interval. Definition. A point P on a curve is called an inflection point if the curve changes from concave up to concave down or from concave down to concave up at that point P. If point P has coordinates C, f of C, and that is an inflection point, then either f double prime of C is equal to 0 or f double prime of C does not exist. Okay, so let's take a look at some examples where we're using the concavity test. Here's one. Find the intervals of concavity and the inflection points for f of x equal 6 divided by x squared plus 3. In the test, we need to work with the second derivative. Okay, and I'd like to know where's the second derivative positive and where's it negative. So I'm going to be building a chart like I was doing in the increasing and decreasing test in order to get my conclusions about where on the graph the function would be concave up or concave down. Let's first get f double prime of x. F prime would be a quotient rule. So, okay, bottom times derivative of the top is 0, and then minus the top is minus 6 times the derivative of the bottom, that'd be 2x. all over the denominator squared. Okay, or that's going to be negative 12x divided by x squared plus 3, the quantity squared. Now I'd have to differentiate again, so it's going to be another quotient rule. Inside the quotient rule, we're going to use the chain rule. So I want the bottom times the derivative of the top, that's negative 12, minus the top, that's negative 12x, times the derivative of the bottom, that's going to be where we'll need a chain rule. We'll have 2 times x squared plus 3 times the derivative of x squared plus 3, that's 2x. And this is all over the denominator squared. X squared plus 3 squared squared would be x squared plus 3 to the 4th. Okay, now I'm going to want to simplify that because I'm going to be setting this equal to 0. So that's why they made such a habit of simplifying, earlier in the book here. Now, let me begin simplifying like this. So here's x squared plus 3, which is in common to these two groups. Let me go ahead and factor out an x squared plus 3 from the two groups, and I'll cancel that with one of the 4 of the x squared plus 3 terms in the denominator. That would leave me with x squared plus 3 cubed in the denominator. Okay, now what's left over in the numerator would be, I'm still going to have another x squared plus 3 times negative 12. Well, that's going to be negative 12x squared minus 36. In the second group, this x squared plus 3 has already been factored out and canceled. You're subtracting a negative, so that means that you'll be adding. 12x times 2 is 24x, times 2x would be 48x squared. Okay, combine these terms, and 36 would be in common. Okay, so you can factor that out. 36x squared minus 36. 36 is in common. You can factor that out, like I said. And here would be our second derivative in simplified form. Okay, set that equal to 0. And you want to solve for x. You can multiply both sides by the denominator. That'll clear out the fraction there on the left. And divide by 36. X squared minus 1 equals 0 means that x squared would be equal to 1, or x would be plus or minus 1. Okay, now I'm going to be building a table like I was doing in the increasing and decreasing test, although this is a totally different test. Okay, I'll be positioning my important values. Now, 1 and negative 1 behave like critical values, but they are not called critical values. A critical value is a number in the domain that will return 0 when you plug it into the first derivative, or it's a number that you can't plug into the first derivative. Okay, critical numbers have nothing to do with the second derivative, but these are still key numbers on the that I'm working with. Okay, so I guess the point of that would be just be careful with the term critical values. Okay, because that's specifically just for the first derivative. So I've got these key numbers here that I'm placed on the number line, and that's going to split the number line into 3 different intervals. And here's my chart template. Okay, interval number chosen, I need to know the value of f double prime, whether that's positive or negative, and then we'll state the conclusion, whether we're concave up or concave down. Once I've got my intervals written, I can then select my test values. So in the first group, I need to select any number I want, just make sure it's in the interval. And by the way, I see more than I should where a student will select a number that is not in the interval. Okay, be careful about that. Like I'll have a student selecting 0, like in this first group. 0 is not in this group. Okay, so that's going to obviously lead to a wrong answer. You can pick any number you want, but what I said earlier, also try to select nice numbers because, you have to do the calculation. And you don't want to be selecting wildly ridiculous numbers, that you got to run to a calculator for or something like that. So like if I were to let x be negative 2 and plug that into f double prime, well, I'm going to have, let's see, negative 2 squared is 4, minus 1 is 3, times 36 would be 108. And then I'm dividing by, negative 2 squared is 4, plus 3 is 7. 7 cubed would be 343. 108 divided by 343, that's a positive. And from the concavity test, if f double prime of x is positive, that means that you're concave up on that part of the graph. Okay, so concave up would be my conclusion. Now I need a number in the middle section here. So a number between -1 and 1. If I let x be 0 and I plug that into f double prime, I'm going to have 36 times -1 is -36, divided by 3 cubed is 27. That's a negative number, so I'm going to be concave down on that part of the graph. And then if I were to let x be 2, plug that in, I'll actually get the same output from when it was -2, right, since you're squaring that number. -2 squared is 4, 2 squared is 4, right, so I'll have the same overall value. And that means I'll be concave up again. I'm concave up on the intervals -infinity to -1 and 1 to infinity, and then I'm concave down on the interval -1 to 1. Okay, open intervals everywhere, just like we were doing with the increasing and decreasing test. Now, where you switch concavity, you're going to have an inflection point. So the fact that I'm going from concave up to concave down, I'm going to have an inflection point at x equal -1. And going from concave down to concave up, I'm going to have an inflection point at x equal 1. If x is -1, and we plug that into the function, we're going to have 6 divided by 4 is 3/2. Okay, and then if x is 1, and we plug that into the function, 6 divided by 4 is 3/2. Okay, and so these are my two inflection points, or these are key points on the graph where I switch concavity. A couple things before I draw the curve here. Number one, make sure that when you're plugging the numbers in to various areas, you know where you're plugging these in. Okay, like I'll have students plug 1 and -1 into the first derivative or the second derivative. Well, you don't want to do that. We already know what happens with f double prime of 1 or f double prime of -1. We get 0, right? Now, what we're doing is we're finding the intervals of concavity for the function. Okay, it's all about f of x. What's happening with the function f of x? We're using the derivatives to get this information, but make sure that you're plugging the values back into the function if you're stating points that are either inflection points or local mins or maxes. Now, also, I've mentioned this already, but make sure that you're showing the work for the table. I will be grading you on the table, and if the table is not there, you're not going to get full credit. Okay, I have point values assigned for creating the table, and so like I said, I'm wanting to see the work there because I'll have students mess up the table, and then they magically have the right answer somehow. Okay, so I want to make sure that you know how we're getting these results here. Make sure that you're showing the work. Well, let's see. If I plot these 2 points, the inflection points, and also if x is 0, I get 6 6 over 3 is 2. By the way, 0, 2 would be a local max. Now, one way that I can see that is because of the increasing and decreasing test. Okay, if I were to find the critical values, I'd be setting f prime of x equal to 0 and solve. Well, if you multiply both sides by the denominator, you'll have -12x equals 0, or x would be 0. X equals 0 would be my critical number, my one and only critical number, right? Because there's no other number that's going to be a problem in the denominator for f prime. So if x is 0, and I plug that in, I get 2. Now, the fact that I'm concave down means that tangent lines are all going to be above the curve, so I can conclude that there's going to be a hill on the graph at that spot, therefore producing a local max. I could also figure out that that's a local max by using the increasing and decreasing test with the first derivative there. Okay, but I guess I just want you to notice that with the concavity test, figuring out where you're concave up or concave down will also allow you to kind of see where there's where there's going to be hills and valleys, producing mins and maxes on occasion. This curve is going to take on a bell shape curve here. And of course, I'm graphing a rational function, right? So I got to pay attention to the asymptotes that would be on the graph. There's not going to be any vertical asymptotes since the domain of f is all real numbers. There's no numbers that are going to return 0 in the denominator. So I have no vertical asymptotes, but I will have a horizontal asymptote at y equals 0, because whenever the degree of the top is less than the degree of the bottom, y equals 0 is a horizontal asymptote. Here, I've got a degree 0 up top, because I don't have any x's up top, divided by a degree 2 down under. Again, whenever the degree of the top is less than the degree of the bottom, y equals 0 is a horizontal asymptote. So this curve is going to be approaching the x-axis, but it's never going to get there type thing. Okay, so again, all very useful information here in order to help me sketch a pretty accurate graph. Okay, and we'll stop there.